Welcome back. If you like this series, please subscribe to the channel, turn notifications on, and give a like. I would like to talk today about non-parametric models. Unlike the parametric models, the relationship between a dependent variable y and an independent variable x may not be known in advance, right? So for example, let's look at this data. It is hard to guess what type of model that it contains, maybe like sine type of terms, cosine, some high order polynomials. And to represent this data or to perform non-parametric model-based least squares linear regression, basically we are going to resort to the neural networks. I covered neural networks in the previous video. If I would like to mention one thing about that, they are a universal function approximators. You can approximate, basically, you can find a continuous function that perfectly fits to this data using neural networks. And unlike polynomials that are also universal approximators, neural networks generally do not suffer from overfitting. And unlike Fourier or Taylor series, which are also universal approximators, they don't suffer from ringing artifacts. Watch this video if you want to learn the advantages of neural networks as compared to polynomials and Taylor series or Fourier series. All right. All I need to do is simple, okay, in this video. I would like to find a non-parametric model y hat. And I am going to choose it to be theta multiplied by w. W will be unknown. Theta is a function which will be our basis. This is unknown weight. And theta will include s entries, s terms, and hence the unknown variables will have s. And as always in your basis function, include a bias, and then the remaining s minus 1 elements will consist of radial basis functions looking like this with different values. At the end of this video, you are going to see a MATLAB example showing how I choose radial basis functions to fit to this data. All right. The formulation here will be super similar to the formulation I do for parametric models. Basically, when you deal with parametric models, let me go back to here. Let's say I know that dependent, like for example, consider this x, this y. Let's say I have data points like this. They look like line. So I assume that the model will be w0 plus w1x. Data has a model looking like the line. It can be it can include x to the power of 2, or like the parametric model video, x to the power of 3. If you can guess the model, it is called parametric model. If not, just use this, include radial basis functions here. This is called non-parametric models. So as compared to parametric models, only how we choose this function will change. Basically, we are using radial basis functions and everything else will remain the same. That's fine. That's why if you watch this parametric model video, the formulation will be quite the same. If you haven't just watched the parametric model video first, again, in this lecture series, every lecture builds upon the previous video, so that if you watch these videos in order, you will understand everything without having a single gap. All right, so since the formulation is similar to the parametric model formulation, I will just give the highlights. We are solving the least squares problem. We would like to minimize this cost function. This cost function includes omega, w, and y. Omega is the unknown terms. W is contains the unknown terms. Omega basically taking these radial basis functions, the first data x1, the second data x2, all the way up to end data. I am assuming that there are n number of data here. And once again, I am using this notation. For example, this data here is the xi corresponds to some yi. This is the first data, corresponds to y1, and it corresponds to x1. I am using this notation in these videos. And theta is an S by n matrix. Y includes all the y1, y2, all the y up to yn, n dimensional vector. If you solve the analytical solution by finding the gradient and setting it to 0, derivations are here. This is the analytical solution, and omega transpose is generally non-singular such that this inversion exists when the number of parameters, data points n, is greater than the dimension of the, or how many radial basis functions you have. Because in this case, omega becomes, since it is S by n, omega is an S by n, its transpose is basically n by s. You multiply a fat matrix by a tall, its transpose becomes tall matrix, such that the end result becomes S by s, and this is generally invertible. Otherwise, it is not true. If you have a tall matrix multiplied by its fat version transpose, then solution, I can guarantee that, will be certainly singular, so that you cannot invert this matrix, and S, so S and N. So it is important that number of data points needs to be equal or larger than the number of radial basis functions that you are using. You can also find this solution iteratively using gradient descent. In this case, the next value of W will be the previous value minus alpha dV, and dV, once you insert dV here again, which is on this video as well, all the details are on this video, and you can find, once you insert dV, you can find the gradient descent solution like this, and make sure that the eigenvalues of this matrix stay on the unit circle. Once again, meaning that this matrix will have S eigenvalues, and they can be imaginary, real. So 1 minus 1, j minus j, all the eigenvalues must remain in the unit circle. This is coming from the property of, under what conditions solutions to discrete difference equations converge. If these eigenvalues are on the unit circle, we call this matrix sure. If so, as k goes to infinity, W will converge to the analytical solution. And previously on these lecture series, I discussed, if you know the analytical solution, why you should find it iteratively. I mentioned my reasons when I covered the gradient descent video. If you haven't watched the gradient descent video, the reason is, very briefly, when you do this gradient descent like this, you can use it online, real time. So it is robust to changes. It adapts to the changes in the data. It can accommodate new data, and it has nice connections to control theory that I am going to reveal in the later videos in this lectures on regression and control. All right, I am going to consider 3 MATLAB examples. I am not going to bother ourselves with the gradient descent. I believe I already did many gradient descent videos or examples, including gradient descent with momentum. I would like to focus on the analytical solution, because we know gradient descent solution eventually will converge to the analytical solution. All right. Here is the basically number of data points I consider, x, and I consider an interesting y function that is looking highly nonlinear, including some noise. X is the independent and y is the dependent variable. Of course, in real life, you don't know this function. That's why you collect some data, and you would like to fit a continuous curve to this data for using least squares. But for the sake of this video, I just created this nonlinear function just for generating these data points that you see here. Okay, I just didn't want to do it arbitrarily by hand, which may not make any sense. All right, so initially I select omega to be 0. Basically, I construct in the first example, MATLAB example 1, I am including a bias and I am including only 3 radial basis functions. Their D1 parameters are the same one, and I want you to focus on these. So the first one is located at -5. The second one is centered around 0. And the third one is around -5 here. I only have 3 radial basis functions, and I am finding the weights, optimal weights, based on least squares coming from this omega selection. Then I am plotting the results from -3.5 to 3.5. I am just generating y hat, like the W transpose, W coming from the least square solution, multiplied by the basis that I choose. And then plotting purposes, you can always stop the video and take the code for your needs. All right, this is not a great fit, so it is clear that using 3 neurons doesn't fit perfectly with this data. This is how I always start, okay? Given a data points, I just start with the minimum number of points. Instead of 5, you can also use 3.5. Results won't change much. And basically, I am using a point slightly larger than my domain that I would like to cover. My domain is I would like to fit perfectly between 3.5 to 3.5, since these data points are changing between 3.5 to 3.5. I just go a little bit off, and I also include a radial basis function exactly to the center. I always start with that, and most of the time this is not a great fit. Then I start adding more. In the second MATLAB example, I am including 2 more radial basis functions, one to the 2.5 and the other one to the, 1 to the 2.5, which shows like -2.5, and other to 2.5, which will appear in here, right? Previously, I only had these 3 ones. Now I added 2 more that are exactly between -5 and 0 and 0 and 5, okay? In this case, this is actually a good fit. I can stop in here. By the way, since you added 2, you also have 2 more once you evaluate that function. I am only showing the plot that contains the changes. Basically, this part of the plot, this part of the code doesn't change. I am only showing the changes in this part, that the additions. I also make this 6 now because the dimension of omega 6 by 40. If you realize, I also I slightly define omega to be the other way, instead of defining s by n, n by s. So I took its transpose in this here, because I mean, you can define both ways. You can also from here include transpose here. It doesn't matter. I just wanted to do it this way. All right. So now, if this is good for you, and honestly, this is good for me, but I would like to emphasize the point that is coming from the neural networks video. I mentioned that if you increase the number of radial basis functions, you are going to improve the accuracy of your least squares fit better. So as you compare the first fit with the second one, just by adding 2 more radial basis functions, this is great enough. Now I am adding 4 more. This time to the point between -5 and to the 2.5. 2.5 to 0, 0 and 2.5, so on and so forth. These are the new entries. So initially I had these, then added to initially I had this, then I added here and here. Now I am adding 1, 1, 1, 1. And we have omega is 10 by, basically it has 10 entries. And I have also changes here in the evaluation. Basically, if you compare MATLAB example 3 with 2, right? If you look at here, there is a little bit off. We don't touch there, we don't touch there. There is a little bit off here and there. But if you look at this case with more increased number of radial basis functions, this is a perfect, almost perfect fit. At this point, you can include more radial basis functions to do slight improvements here and there, but engineering I cannot see. I think to my eyes, this is a great fit, and radial basis functions greatly captures this data perfectly. Now, right, when you want to learn something, you should code things yourself. Start from the first code. Let me give you an homework, if I may. So instead of using -1, -1, -1 for the D1 weights, D2 weights, change it. Try -2, -2, -2, or -0.5, -0.5, -0.5. And tell me which one is better. Experience yourself. I don't want to give the solution, but intuitively, I am using neural networks for more than 15 years now for different areas in control, machine learning and regression, estimation. And I can tell you that if these values are high, like -5, -5, -5, your fits may not be great. I usually tend to select them to be -1, -0.5, -0.2, 0.1. So in this, they tend to work better. Basically, radial basis functions, if you choose them to be -1 or -0.5, fits will be much more smoother, and you are not going to see interesting spikes here and there, but experience this yourself. Please experience this yourself to deepen your understanding. All right, thanks.